This is a chemical reaction in action. It's happening right now. Iron reacting with oxygen to form products. This is also a chemical reaction in action. In this case, it was propane reacting with oxygen to form products. And this particular one was in Brampton a few years back, and I think several firefighters died trying to fight that place. But if we look at it from a chemical point of view, what's actually different about those two reactions? They were both reactions with oxygen, and they're both reactions producing products. So we have a lot in similarity. But what's different? Well, obviously, from the point of what we could see, but also from a chemical point of view, the reaction rate. In other words, how fast were those products being formed? That car could have been doing that reaction for several years, whereas that propane fire probably would have burned itself out within several hours, but of course we wouldn't want that to happen in that way. The other thing that's different between them is the amount of energy that's released. Now, I want you to think about that in terms of energy, in terms of what we know about energy. Because when we say energy is released, we have to remember the law of conservation of energy, because that tells us that, and I didn't write the whole thing out, and you don't need to either, but energy cannot be created or destroyed, it can only change form. So if energy is being released, it's got to come from somewhere. And that becomes one of the questions that we need to start asking is, when we're looking at chemical reactions that involve energy, where did the energy come from? Or another question we could ask is, does every reaction do that? Does every reaction have some sort of energy change? Like that car, is energy being released during that reaction? And the other question that we can ask is there energy going in to some reactions? Do I have to provide energy for some reactions? So in other words, maybe energy is not always released. I want you to think about a chemical reaction in terms of a circle. And let's draw a schematic here. And that circle will be what we call the chemical system. And that's going to be a phrase that we use a fair bit in this unit. And then around that system is the surroundings. And the surroundings is, well, really anything else, but we can sometimes have a bit of control on them. So the air around it, the container that it's in, if you're holding that thing and you can feel an energy change, then you would be part of the surroundings. And then we have two options. So we'll look at a left half and a right half. One option is that energy, as we mentioned before, can be released. So energy is leaving the system and going to the surroundings. And we actually have a term for that. You may remember from another course, we call that exothermic. Energy is exiting the system. The other option, of course, as we mentioned, we didn't really answer the question, but energy could be going in from the surroundings into the system. And that we call endothermic. And again, terms that you may have seen before, perhaps you remember, hopefully you do. If not, you're going to get lots of practice with them this time. When we talk about energy changes in a chemical system, we want to quantify it, we want to make it, say, somewhat standardized, we end up talking about something called enthalpy. In enthalpy, we give the symbol H. And H, we're often going to use the term heat. So energy changes can often be in terms of heat energy changes, because I can measure heat energy changes. So whether that's where the H comes from or not really sure. But enthalpy is the word, H is the symbol. What is enthalpy? Well, enthalpy is the total amount of energy in a system. The problem with that is we can't measure total amount of energy, because we can measure bits and pieces, but those molecules have motion, that's energy. Even if you think about the planet revolving and then going around the sun, all of those bits and pieces are parts of the total amount of energy. What we can measure is change in enthalpy, and that's our delta H. So delta H, the triangle, that is the change in energy. Because if we assume that the other bits and pieces, the planet going around and around, although those other aspects that we cannot measure accurately, if those stay constant, then all we have to really worry about is the change in energy. For us, that change in energy is going to be determined by doing a subtraction between the energy possessed by the products and the energy possessed by the reactants. And when we do that, we'll have our change in energy. Now I want you to think about this. If the if the reaction rather released energy, how does the energy of the products and the reactants compare? If the system absorbed energy, how does the energy of the products and the reactants compare with each other? And for us, almost always we're going to be expressing the total energy, or in other words, the enthalpy change, in terms of moles. So something amount of energy per mole. So I hope you remember how to calculate moles and molar masses and things like that, because that's coming back. So let's think about the chemical energy in a reaction. We had two kinds of energy transitions. I had put up 3 fingers, didn't I? 2 kinds of energy transitions. One was exothermic. And in an exothermic reaction, energy is being released, which means the chemical energy of the system is going to decrease because some of that chemical energy is going into the surroundings in the form of heat. So when you notice an exothermic reaction, you'll feel things warming up because chemical energy is being released as heat. Remember that delta H. And then it's released into the surroundings, which you might be a part of. On the other hand, the endothermic reaction, energy is being absorbed, so the energy of the system increases during the reaction. Now, the strange thing about endothermic reactions is that since you're on the surroundings, if that system starts taking energy in, it's going to take it from you. So what you'll notice is the temperature starts to drop down and it starts to feel colder. But it's going into the system not as heat energy, but it's being turned into chemical energies. It's one of the reasons why that still ends up working. Well, how do we represent that? Now that we understand that we can have energy lost or energy gained, how do we actually show that in a chemical reaction? There's actually 4 ways we're going to use, and sometimes we'll use one over the other, and so on. They're all useful, they all have value, we will use them all. One of them is to use something called a thermochemical equation, and I'm going to show you examples of these in a minute, so you don't have to necessarily write it down right now. We can also have reactions with enthalpy terms, and I'll show you what that means in a couple of minutes. We can have a potential energy diagram, very graphical kind of thing, although for us we're not very often going to have that thing to scale, but it will represent something. And then we can have enthalpy tables, and enthalpy tables are actually really, really useful, but they're probably the hardest to get used to. So let's take a look at each one in turn. Thermochemical equations is really just a chemical reaction with the energy term added in. So for example, it might look something like this, and that would be an exothermic reaction where energy is coming out. I don't want you to think of it as a product, even though we can say energy is produced, because when we talk about products and reactants, we're talking about chemicals. But energy is definitely coming out of that reaction, similar way to the products come out. As a specific example, I can take a look at this, a combustion of methane. I should have used propane, where the energy comes out and we actually have a number for it, 889 kilojoules. If I doubled everything there, so right now I've got the imaginary 1 in front of methane. If I had 2, I would have twice the amount of energy. On an endothermic reaction, energy goes in, much like the reactants do. Please don't say that energy is a reactant. Okay, it's on the same side as a reactant, but reactants are chemicals and energy is not a chemical. As a specific example, I have here where if I want to take the water out of, you remember from grade 11 nomenclature, that would be calcium chloride dihydrate, water trapped in the crystal structure. If I want to get that water out, I have to put energy in. And that would take about 180 kilojoules each mole of that I use. Reactions with enthalpy terms is actually going to look fairly similar, except the enthalpy term is going to be tucked off on the side, labeled as delta H. So using the first one again, I have the combustion of methane, and then you'll notice that off on the side here, I have the delta H equals negative. Now negative because the energy of the products is less. If it's products minus reactants, then it's smaller number minus big number, I end up with a negative value. And the endothermic one would actually have a positive value because the system is gaining that much energy. Potential energy diagrams, we'll think of start with thinking of a graph. And on the up and down axis, that we call the y-axis, we have potential energy. On the horizontal, the x-axis, we have time, or basically as that reaction proceeds. The reactants are going to start out with a certain amount of energy, And in some exothermic reactions, the products will finish with a lower overall amount of energy. And then, of course, the missing energy went into the surroundings. The decrease in energy, the gap between those 2 points, that will be the delta H value. Now, obviously, this is not to scale, although I suppose it could be if we knew what the scale was. Conversely, if I had an endothermic reaction, it would look something like this, where the reactants start out with a certain amount of energy and the products have a higher amount. Finally, we have enthalpy tables, and it's hard for me to show you an enthalpy table here, but there are some in the textbook and there's lots of other sources for them. But it would look something like this, where you would be told a particular kind of chemical process. So in this one, combustion. As soon as you hear combustion, as a chemistry student, you should be thinking, okay, reaction with oxygen to produce these products. So as soon as I say combustion, I already have the chemical reaction sort of in mind, and then all I have to say is things like, well, for propane, this much energy is released. For propanol, a different amount of energy is released. Conversely, I could have that molar enthalpy of vaporization. Vaporization means converting from a liquid to a gas. So not actually a chemical process, but a physical one, still having a difference in energy. As soon as I know it's vaporization, I'm going from a liquid to a gas. I have the process in mind. Now all I need to know is that for this compound, water for example, it requires 40.8 kilojoules per mole, and for ethylene glycol it would involve more. Well, what do we do with that, or how do we get those answers? Let's go back to this and think about our system surrounding the energy transferring in. If I try to isolate, or let's say insulate the system into surroundings that I could control much more easily than just the air or my hand, and then I took a thermometer and plopped that in there. So I now have highly controlled surroundings. If I were to measure the temperature change of the surroundings, where did the energy change come from? Well, if the energy change of the surroundings is, well, let's say the temperature goes up, where did the energy come from? It came from the system. Let's say the surroundings goes down in temperature, where did the energy go? It went into the system. If I know the energy change of the surroundings, I can calculate the energy change of the system. And we call that calorimetry. And we're actually going to be doing some calorimetry. We're going to do a fair bit of it, actually. And in order to do it, in order to relate temperature change and energy change, I need something called the specific heat capacity. By definition, specific heat capacity is the energy required to raise the temperature of 1 gram of stuff, so any substance, irons, cobalt, nickel, lead, water, raise the temperature of 1 gram of substance by 1 degree Celsius. Now these, as you can imagine, have been well worked out for a long time, so we actually know specific heat capacities of most things. And then we use that to figure out the energy. So turning that definition into a chemical formula, we have that, not a chemical formula, a mathematical formula, but then we rearrange it so we're usually solving for energy. So the energy is the specific heat capacity of something times the mass of that stuff times the change in temperature. So if I have 10 grams of water and it went up by 5 degrees Celsius, and I know the specific heat capacity, I know how much energy that took. And then what's going to happen is we use that to figure out what happened to the system. So any energy lost by the system will be gained by the surroundings. Turning that into a mathematical thing, that means if one went up $10, sorry, not $10, if one went up 10 energy units plus 10, the other one went down, it went minus 10. To keep those actually equal, we change the sign of one. So the energy of the system is equal to the negative energy of the surroundings. That's going to be our basis for calorimetry. And of course we know that the energy of the surroundings we have from here, because that's where our thermometer is. Anyhow, that is the basic starting point. We'll take care of a lot of that math in class, so you'll have your calculator. We'll do some lab activities involving all of this, and we'll become calorimetry experts before you know it. Talk to you in class.